Hi everyone, my name is Santiago and today we're going to be looking at a pentest report done for DNSmasq. And if you ask where I found this report, I can tell you that I got it from pentestreports.com. This is the website or one website that I have developed and has over 200 reports available for you to read online, so you can go through the pages, download the PDF file, and also you can find tons of other information, commands, companies, cybersecurity companies, and so on. Anyway, back to the report. It's an old report from 2016, but the reason I decided to cover this on a video is that DNSmasq is still being maintained, and second, is a tool that I like and that I used a few times before, especially when I needed wildcard DNS on my local network. And third, well, it's a report that is not too long, 10 pages in total, so it's not unreasonable to cover on a video. So this was commissioned. Well, first of all, so if you don't know about DNSmasq, that is a software open source that provides network infrastructure for small networks. So I use DNS, or I use DNSmasq for DNS, and DNS is on the name, but also DHCP and router advertisement and other things that this software can do. And the report was commissioned by SOS program run by Mozilla. SOS is secure open source, and it was done by the Cure53 team, a German team, security team that does the same for many other, or have done the same for many other open source projects. So it's really good. Okay. What else? By the way, this annotation, the highlighting, is done by me, the yellow bits. Okay, let's scroll down. So this report, done again by Dr. Mario from Cure53, was done use some tool assisting code auditing. So it's somebody, the person Mario, looking at the code, but also using some tools to find different things that are included in the report. Okay, what else? DNSmasq, the code, is not on GitHub like most of the other software today is, or open source is, but it's on one family website under the kellys.org.uk domain. So Kelly is the surname of the family, or the family surname, and there is a Git repository where you can find the code. Okay, so first finding, which is buffers that are not initialized, and that can lead to a memory leakage. So here it says it was discovered that the application does not properly initialize the buffer for incoming and outgoing packets, and this leads to a partial disclosure of previously received or sent packages. Okay, so in essence, what this is explained here with an example. You can see the victim sends, and this is of course just for demo, the content does not need anything. So here is sending leak me 91 times, so almost 550 bytes to the server, to the DNSmasq server, using UDP. That's what -u does to NCAT or NenCat. So it's sending almost 550 bytes to the server, and then another client, this time the attacker, not the victim, sends another request to the server, also UDP. Oh, by the way, the first one was port 53, so that's DNS. Second one is port 69, which is TFTP, so trivial FTP. And it's asking for a file, and here it says the file is not available. So the server comes back to the attacker, not only with the message the file is not there, but also with the leak me that it was sent by the victim to the server. So that's the vulnerability. So it's sending more information because the buffer that the server uses was not properly initialized and clean in between connections. So yeah, here is the breakdown of the vulnerability or the problem. So it's evident that the message sent to the attacker should by no means contain data sent by the victim. The vulnerability is caused by two different flaws described next. So the first one, there's no initialization. So there's part of the code that has a buffer and a structure that is not initialized. So it could contain anything, and in between connection, again, the memory is not clear. So the buffer might technically contain all data, and that's indeed the case here. So for a new connection, it was returning information from the previous connection. Okay, so that's also happening. The above is also happening because the code is using snprintf, but it's using it wrong. It looks like the authors of the DNSmasq code understood the return value of the snprintf function as the number of bytes written or print, when in reality is returning the number of values that should have been printed if there's enough capacity in the buffer. So here's snprintf returns the number of bytes that could or should have been written if there was no limitation in place. So I can also show you where that's coming from. If we go to the return, where is it? Here. So if the output was truncated due to this limit, then the return value is the number of characters which would have been written to the final string if enough space had been available. So that's coming literally from the man page for snprintf. Okay, so we said at the beginning or earlier that the attacker calls the server asking for a file that does not exist, and the server sends an error message and the leak information. So the error message and the problem with snprintf is here. So there is a function called tftp for trivial FTP error. Oops. And again, it's making use of snprintf, but it's not using the right use, or not making the right use of that return value. Therefore, again, returning not only the name or the content of the error message, but also a bit more. Okay, so that was the first finding, quite an interesting one. Second, by the way, the severity for the first one, I think, was medium. Don't remember now. Yeah, medium. For the second one is low. So here, the make file lacks security parameter for GCC. So GCC, the new compiler collection, also the C compiler, can be given a flag to compile with position independent executable or not. And in this case, DNSmasq is not being compiled with the position independent executable, which makes predictable where the memory is going to be mapped, or the executable, the binary is going to be mapped. So here it says, so for memory maps without pi, the position independent executable, it starts here, which is the default address on 64-byte Linux systems. Now, if you compile with pi, then the position is going to be random every time. So that's a benefit. Of course, makes things harder for people who are trying to break the the application. And there is a way, of course, to check this. Say, for instance, if I create a very simple C file, you can I have compiled my test file, so I have a binary, and if I do readelf headers, tells me position independent executable. I can also say, and because it's okay, so there's more I can show you. So if I do scanf, I'm going to save that. Let's use DNSmasq. So that's going to be hanging there. So I can grab the process ID, the PID, and do an proc and you can see the memory address is completely random. Now if I compile this with no position independent executable, and run it again, of course the process ID now is different. You can see the first address is that one, 400,000, as the document was telling us. So that's a minor problem, but it's still one thing that the Cure53 team recommends to address. Okay, what else? Then we have this that is essentially saying that we are asking to resize an array, a buffer, but we are not checking if that's successful. So we can make the application crash, of course. So here we are assuming that the system is going to give the program more memory. That typically is the case when we are asking for small amounts of memory. But if you are asking for a large amount of memory, the response can be null. Or if there are many other applications in your system that are asking for memory, so there's nothing left for you, even if you ask for little. So again, it's low severity, but something that the Cure53 team recommends to address. More of the same, again making the wrong assumption about the return value of snprintf. And what else do we have here? Okay, here you have these scanf functions again, and well, it's using a file descriptor and the format of strings that says I want to read the strings of a maximum of 255 characters long or bytes long, and same here, 64 characters long, 255, 764, and the buffers here, name buffer, the HCP buffer, and the packet buffer are big enough to hold these strings. But what this is saying is, well, because this is hard coded, if you change the buffer size and you make them smaller, for instance, you could be doing a buffer overflow, essentially. So you could be writing beyond the capacity of those buffers. So what they recommend is to have these numbers, the formatting or the strings to come dynamically, to be injected dynamically. So instead of assuming is going to be the same, then make it dynamic. Because it's easier in the future for somebody to change the buffer size without changing these hard-coded strings, and then the problem comes. Anyway, so that's pretty much it. So conclusion, overall positive, the review from Cure53. So they say DNSmasq has a secure, mature code base that they only need to make this small adjustment to make it fully secure. And that's it for today. If you like this content, please subscribe to the channel. I'm going to be covering more tools and more pen test reports in the next days and weeks. Thank you very much. Bye bye.